Welcome back, folks. Today we are going to take a look at the ideal gas law. So we've taken a look at quite a few different gas laws already. We've talked about Boyle's, Charles, Gay-Lussac, Avogadro's law, the combined gas law. What we're going to do now is take a look at kind of all of those things combined together into a gas law that works specifically under ideal conditions. Now, realistically, not all gases exist under ideal conditions, because with ideal conditions we take into consideration that the molecules don't collide with one another and they don't exhibit any intermolecular forces, and we know that for the most part that's not true. But we use the ideal gas law because it's a very good estimate of how some of these variables change based on the variables we do have in a gas. So today's goals, you should be able to evaluate the ideal gas law and understand how to perform calculations specifically related to ideal gases. We only have one key vocabulary term for this, and that is the ideal gas law. So all of the gas laws previously discussed can be combined into one simple equation to describe the mathematical relationship between all of the different variables of a gas. Now again, not many gases are truly ideal gases, but this gives us, like I said, a pretty good estimate of how some of these variables behave. And this equation is P times V equals N times R times T. Now P is representative of pressure, V is volume, N is the number of moles, T is temperature, and R is what's known as the gas constant. That's a constant value that will always be given to you. So you'll always use the same gas constant. Now keep in mind that that gas constant can change depending on what types of variables that you use. So we may need to alter some of the variables or use dimensional analysis to be able to get them into the units we want so that we can use the proper variable R. Again, just a reminder, so for example here, P, pressure, which is measured in atmospheres, V, volume in liters, N is moles, R is the gas constant, and for the variables that are listed here, the gas constant is 0.0821, T is the temperature in Kelvin. Now keep in mind, you may need to adjust your variables before solving, so I may give you pressure in PSI, and then you would have to convert that to ATM to plug into your equation. Volume may be given in milliliters instead of liters. Instead of moles, I may give you grams or atoms. Temperature I could give you in Celsius. So albeit it looks like a pretty simple equation, and it is, you need to make sure that all of your variables are in the correct unit in order to proceed utilizing the ideal gas equation. Alright? Other than that, I give you 4 variables, you solve for the one you don't know. So let's take a look at an example of a practice problem. What is the pressure in atmospheres exerted by a 0.500 mole sample of nitrogen gas in a 10-liter container at 298 Kelvin? So let's take a look at the information that's given to us. We're given the amount of moles, we're given liters, and we're given temperature. And what the question is asking for is pressure in atmospheres. So for this, we're going to use the equation PV equals nRT. Now, one question I get asked a lot is, how do I know the difference between when I'm going to use this and when I'm going to use the other gas laws that we discussed in the previous video, like Boyle's, Charles, combined gas law? If you notice in this equation, it doesn't say that anything changes. You're not given 2 pressures or 2 volumes or saying that something's changed and has increased in temperature or something along those lines. With this, you're essentially given one of each variable. With some of the others, you're given at least 2 different values for pressure or volume or some variable there. So when we do PV equals nRT, nothing changes. When we use the combined gas law, some stuff is going to change. So just kind of keep that in mind as we go through this. So we need to know our equation, which is PV equals nRT. P is our unknown. That's what we're trying to get at, so we'll call that X. V is our volume, which is 10.0 liters. And that's in the proper unit that we want. N is moles, which we're given 0.500. That's good. R is our gas constant, so that's 0.0821. And our temperature is given already in Kelvin, so that's 298. So this is already set up pretty easily for you guys. Now keep in mind, some of these variables may differ. You'd have to make sure to convert them into, whether it be atmospheres, liters, Kelvin, or moles. So let's plug this numbers in and solve. So we're going to have xp times v equals N times R times T. Now all we just do is we just plug it into our calculator and algebraically solve for x. So we'll multiply everything on the right side and then divide both sides by 10, isolating x by itself. Significant figures still apply here, so we want to make sure we use 3 significant figures in our answer. So therefore, x is going to be equal to 1.22, and the unit for pressure in this instance is ATM. Simple enough. So again, just plug in your variables and solve, and if your variables differ from atmosphere, liters, moles, or Kelvin, then you just need to convert them into what you need. Let's do one more practice problem, just to make sure. A 4.44 liter container holds 15 grams of oxygen at 22.55 Celsius. What is the pressure? So, again, let's take a look at what's given. We're given our volume, we're given a mass, and we're given temperature. So remember with our equation, we're going to use PV equals nRT. And the question again is asking for pressure. So let's see what we got here. We've got P, which again is our unknown, so we'll call that X, a volume, 4.44 liters, N. Now we are not given moles. However, we are given grams of oxygen. So we need to convert that into moles of oxygen. 15.0 grams of oxygen. Now remember, oxygen by itself is not O, it is O2. Remember, it's part of the diatoms. We need to get it to moles of oxygen. So grams goes on the bottom of the next step. We can convert to moles. To go from grams to moles, we're going to use the molar mass, which we find on the periodic table. Molar mass of O2 is 32. So we do our calculation, and we'll get our number of moles. So we're going to have 0.469 moles. Our R value, 0.0821. And our T temperature is given in Celsius. You know we can't use Celsius, so we're going to need to convert that to Kelvin. And to do that, we take Celsius, and again, we add 273.15. So then we'll get our answer in Kelvin. So our temperature is 295.7 Kelvin. So now all we need to do is plug those variables into PV equals nRT and solve. So P times V equals N R T. And again, we just plug our numbers in and we solve for X. Our answer should have 3 significant figures. So our pressure is 2.56 ATM. Okay, simple enough. So again, some of these issues we may need to go through and convert them into the units that we want. But you already know how to do that, so I don't anticipate any problems with this. So, long story short, the ideal gas law represents a mathematical relationship between pressure, volume, temperature, and the amount of a gas. Again, the system is not perfect and doesn't really specifically describe a real gas, but we utilize this equation because it's a good estimate of the relationship between all of these different variables. Hopefully you got all the information you needed from this video. I will post a word of the video somewhere previously. You'll find it. Anyways, have a great day, guys. This is Jalen Bio. We'll talk to you later. Bye-bye.